Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Paul Johnson and Tuan Vu with us today. Hey, Tuan. Hey, Paul.
Hey, how's it going?
I am doing very well on this August 18th of 2022 as we shoot this one. And Tuan, where are you located at?
Hi, Frank. I'm currently in Pasadena in my office at JPL.
It looks very sunny and nice outside your window.
Very hot too.
Very hot. What is hot in Pasadena?
Right. You know, I'm sure certainly comparable to Phoenix, I guess.
Oh yeah. So I went to the AAS 240 and we just had that in Pasadena in June. And I went there and it was like 95, 96 F and everybody, oh, it's so hot. It's so hot. And I'm going, this is cool. This is fantastic. I don't know what you guys are complaining about here. This is wonderful. And Paul, you're also at JPL, Caltech?
Well, I'm in Pasadena, but I'm at home today. I had a back-to-back Zoom meeting, so I decided to stay home, but I'm still in Pasadena.
Okay, very good. Awesome. Hope all goes well. Cool. Yeah, so Paul, what do you like to do for research?
The last number of years, most of my work has looked at physical chemistry of ices, cryogenic ices that relate to surfaces in the outer solar system. So we do lab experiments trying to understand the chemistry of outer solar system ices.
Very cool.
Yeah.
What you like?
So I'm a research scientist here at JPL. I do a lot of experimental work on planetary ices system. That means low pressure cryogenic, and I do a lot of organic analysis for Titan application and frozen brines chemistry, which we'll talk about today, and clathrate hydrates, which is something I've also done a lot of work on since graduate school.
Very cool. Very cool. And that is going to bring us to this very awesome Planetary Science Journal. It's open access, people, so go grab a copy for free. And formation of vitreous salt hydrates under conditions relevant to Europa. And Paul and Tuan, take us away.
Okay, I guess maybe Tuan, if you want, I can sort of start with sort of the intro sort of blurb, where we got here and why we're doing this kind of stuff. So over the last, I don't know, 5-6 years or so, Tuan and I and a couple other colleagues at JPL have been doing a series of experiments where we're basically looking at how brines freeze and what salt minerals form when they freeze, with the idea being that if you have an ocean world like Europa and the ocean fluid gets onto the surface, freezes, and we can see the surface, we see what minerals are there. Are we able to sort of make meaningful linkages from the surface mineralogy back to the source brine composition, in terms of what ions are in there and what concentrations, or, what can we actually learn about the ocean composition with, indirectly from looking at its expression on the surface?
Cool. Got it.
So in a sense, it's kind of, I don't know, maybe sort of simple experiments in some ways where we make brines, we freeze them, and we look to see what we get. But we've been playing a lot with this kind of a putative Europa ocean brine, where we're using sodium, magnesium chloride, and sulfate, and that's largely chosen, to get it to a sort of tractable problem, where we don't have like 1,000 different components, where we, but one of the things that we've noticed, or that we discovered while we were doing this, is that in a lot of cases we would look at these cryogenically frozen brines and see that we were forming vitreous or glassy salt hydrates, which initially was sort of I guess maybe a bit of a confounding thing, because we were looking for the crystalline Raman signatures or whatever, and not seeing them, and seeing these kind of broader or shifted features. But got us sort of thinking about it, and there's been an idea that's been put out before in the literature by other people that have seen glassy salt hydrates in research related to Mars and Enceladus, etc., where they pointed out that A glassy material might be something of interest for astrobiology because
Okay.
if a large molecule or even a microorganism is entrained and frozen in a glass versus a crystal, they can be preserved because they don't have this physical damage that is caused by the crystallization mechanism. So when you get things crystallized, you actually get like cell lysing and stuff, and just like
Right.
so then there's this interest, we had this interest, well, is this a place, if we're seeing these glasses, does this suggest that if we should be looking for glasses on places like Europa, and then looking at those samples for evidence of life from the ocean below? And so that sort of brought up, I guess, sort of three kind of questions in my mind, or our minds. I shouldn't just attribute it to me. Number one is, we were seeing these glasses form when we saw flash frozen fluids. So that's kind of an extreme freezing scenario, which may be applicable to something like a plume, where liquid is just jettisoned into space in tiny droplets and freezes next, relatively, or not relatively, very fast.
Yeah.
But then that would suggest then perhaps a somewhat limited application of this idea, because you'd have to find these kind of plumes, these flash freezing. Where is flash freezing appropriate?
Right.
So then we thought, well, how are there, can we explore the range of sort of scenarios over which these form, and therefore potentially broaden the applicability of this thought to different areas of ocean expression that haven't gone through this extreme flash freezing sort of scenario.
Cool.
And the second one that and sort of we'll get to later is if these things are forming relatively common, then are they stable on the surface? And then the next question is is this idea that they help preserve things really true or not? So that's sort of kind of moving into the future. But in this paper, we basically took that first problem and said, over what range of conditions can we, or will we see these glasses form? And thus, how broadly applicable is this idea to surfaces on, ocean worlds in the solar system?
Good, cool.
So I guess that's where we are. That's where we got started with this. So this, the experiment's kind of a fairly simple one. We basically take solutions of known concentration. We have a cryogenic sample stage for our Raman microscope. And basically this holds just a microscope slide that we can deposit an aliquot solution on, and then cool it at a controlled freezing rate. We can then examine with Raman spectroscopy to look for signatures of either crystalline or amorphous or glassy forms of the salt. And then we just sort of did this over a range of concentrations and freezing rates, and kind of tried to map out, for a given concentration, how slow can you freeze something and still get a glass to form. And then, sorry, go ahead.
Does the experimental apparatus allow you to control the pressure as well? So PNT?
I'll let you go, Tuan. Why don't you jump in?
Sorry, I'm just asking a random question.
Yeah, no, that's a good question.
Yeah, that's a very good question. So the apparatus that we currently use allows for experiments at 1 bar, and certainly, this is the first step, where we just do it like, the easiest way possible.
Sure.
Later on, when we get a handle on them, then we can begin to do experiments under vacuum that makes it even more applicable to Europa. Just one note, I'll add to what Paul was mentioning, is that reason we use Raman spectroscopy to study this glassy material is that it's arguably one of the most sensitive technique for this kind of application. If you're familiar with Raman, is a complementary technique to infrared, in the sense that it probes the vibrations of the molecules in a certain chemical environment. So some modes are IR active, Raman inactive, and vice versa. So for some molecules, it's good to use IR for water, ice, and salts. In particular, Raman is good because those have a very strong infrared absorbance, so you don't see much. With Raman, you can detect the vibration of the molecules within the ice matrix. So that's why we use them. Just for future application of a possible lander to Europa, a Raman spectrometer has been considered part of the Raman payload on the lander, and so this would this kind of study not only helps us establish the chemistry of freezing brines, but also sort of lay some groundwork for future application on lander. So
yeah, I think that'd be so cool if we took a Raman spectrometer to Europa. That would be great.
Yep. And so so I think Paul has described the experiment. Basically, so I think we can go and look at some of the results. So let's scroll to figure 1, and that'll show you some an example of type of data that we gather. Yep. So in this figure, we're freezing a 2 molar magnesium sulfate brine at 100 Kelvin. The blue trace is when the brine is flash frozen. That means we put a droplet of brine directly onto the cold stage and instantly froze it.
Yep.
The red one,
sorry, Tuan, I forgot to mention that is I talked about slowly freezing things in the cryo stage, but when we can do the cryo stage allows us to do controlled freezing rates as fast as I think it's 50 Kelvin per minute, and then we can't control the freezing rate faster than that. But we can do a flash freezing experiment where we basically pre-cool the stage to 100 Kelvin and then put a drop on it, a 5 microliter drop on it, and then it freezes over quite instantly. And that's what we're calling a flash freezing here.
Okay, good. Thank you.
Yep.
Sorry, go ahead, Tuan.
And the blue trace.
Yep. Yes. So that's the blue trace is when you flash freeze the brine. The red trace is when you put a drop of liquid brine onto the stage and slowly freeze it down to 100 Kelvin. Okay. And in this particular case, we freeze it at 20 degrees per minute, which is which is still considerably fast in some cases. But in this instance, you can clearly see the peak that you're looking at in the inset at 985-ish. Yes. That's the symmetric stretch of sulfate. Okay. And so in the blue trace, you can see that it's pretty, it's relatively broad. The full width half max of that is about 10 wave number. And in the red one is about 4 wave number, and this slightly shifted to the right. This is in this case like 999. 990. So 990 a peak at 990 in the Raman is indicative of crystalline meridianite, which is magnesium sulfate 11 hydrate. Okay. So in this case, we have in one experiment a crystalline sample, the other one is a glassy sample. So this peak, this sulfate peak at 990 is probably the most characteristic feature that tells you what hydrated state you have, whether it's glass or crystalline. And then along, with the sample, it's worth keeping in mind that this is, not just the sulfate salt in the sample. You have a lot of water around it. This is only a 2 molar. Well, I shouldn't say only. 2 molar is pretty salty, compared to ocean water here on Earth, of course. But in the context of a solution, water is 55 molar. So you still have about 30-fold more water than salt. So where's all the water? So that's what you see on the right part of the spectrum. So that's very strong peak at 3100. That's water ice, it's actually, the entire broad region between 3,000 and
3,500 or something, 3,600.
Those are all the water ice there. Yeah.
Okay.
So, yep. So the water ice in this case is crystalline. And so we do not make amorphous ice in any of these experiments. Amorphous ice is rather hard to make. And so it's worth keeping in mind as we go along that the samples we have is a mixture of crystalline ice plus, crystalline or glassy salt. So yeah, so that's on the 2 molar solution. So now if you go back to table 1.
Yeah.
So we basically, repeat this experiment over a range of freezing rate and determine basically the critical point at which you cross into the crystalline versus the vitreous
always too small
formation. Okay. So in this particular case, when we get to 30 degrees per minute freezing rate and above, you tend to make glass. Below 25, we consistently make crystalline.
Yep.
And so you notice that I left out the entire region in between, and that's sort of a gray area. So
right.
We're going to go into this a bit more, please.
I'm sorry, one more time.
Yeah. Paul, I can take you to why this
okay,
is
yes. So basically, I can see we're starting to step through the freezing rate at a fairly fine half degree steps. So we're kind of getting into this sort of experimental limit about how well we're really controlling our temperatures, etc.
Right.
And so when we're passing through this kind of if you want to call it the critical temperature, where you pass from, or critical rate where you pass from glass formation to crystal formation, we're sort of hitting it or missing it. And so within this like 1 or 2 1 degree, we see we saw at 27 we got a crystal, and then at 26.5 we got glass again, and then when we did 26 we actually were started to observe it as a glass, but as we were taking spectra it transformed to the crystal. So we sort of, it sort of sets sort of the limitation of the resolution at which we set this freezing rate boundary. But for I think for practical applications, if your freezing rate is around 26, then I think we're sort of up in the air. But if you're like 20 versus 30, you know what to expect.
Right.
So I think that's sort of what you get out of that. And then I guess we could go. Okay, so this is the mag sulfate 2 molar solution that we were just looking at in figure 1. So that's the spectra we would be seeing, that where we identify things as being glass or crystal. Now I guess you could go to table 2, which is right below it. So this is the same salt, but with a lower concentration. And what you see, what happens here is that we are able to get glasses forming at significantly lower freezing rates. So you're seeing that with a lower concentration, it's easier to form the glass.
Okay.
Just sort of an interesting observation. And then let's see, we probably maybe go to want to go to figure 2, Tuan, and change the salt?
Sure, let's do.
And I'll let you describe the figure, Tuan.
Figure 2, and here we go, Raman with the 2 mol.
Yep, so you've seen the results for mag sulfate. So when, as we were doing this sort of experiment over the years, we concentrate on magnesium sulfate chloride and sodium, which is, which are the likely constituents of Europa's ocean. So we've seen that mag sulfate can form glass, and so we started, also asking the question, and could other things also form glass by itself, which is like, quite a natural thing to ask. So similar to the first one, we look at a 2 molar brine of magnesium chloride, and so the blue and the red again are similarly color-coded. The blue is a flash frozen solution. Red one is the slow freezing at 20 K per minute. This case, you probably don't need to explain much, but you can clearly see a stark difference between the spectra.
Very.
one being the glass, the other one is
Let's do that.
crystal.
Yep.
Yeah. And so unlike the sulfate, which has a molecular vibration within the ion that you can see, chloride doesn't have that. It doesn't have that vibration. So you have to see it through its perturbation to the water region. So the most apparent one is the 3000 to 3600 region. So as I mentioned before, this region is water ice. Yes. And so you can see the sharp spikes in the red one. Those are the perturbation of the chloride ions onto the water. That gives you those interesting peaks. And so this is how we can tell that magnesium chloride in this case is crystalline. And you can also see a little bit of that in the 100 to 300 region. It's also quite sharp. So that region is typically the lattice vibration water, which when you have magnesium chloride binding to the water, it's going to look different than just water by itself, and that's what gives you those features over there. So similarly, table 3 shows you the freezing rate that we went through for the 2 molar mac chloride. So in this case, the only time when we manage to see the glass formation is when we flash freeze. Okay. Anything below 50 degrees, which again is the limit of our experimental apparatus, make crystalline. So somewhere between 50 K per minute and flash freezing, there's a region that we can make vitreous microlite. But we are unable to determine, to exactly pinpoint that at the moment. But
Tuan, just for interest sake, just flash freezing, there's some discussion about estimates of what that actually is in terms of a freezing rate, and instead of being like tens of Kelvin per minute, it's tens of Kelvin per second, just to sort of it isn't really instant, but I mean it's that sort of change in magnitude.
Good.
Yeah.
Good.
Okay, sorry, go ahead, Tuan.
Yep. And so just like when we did with matte sulfate for the macrolide, we also decreased the concentration of the brine just to see if we can manage to catch where the transition is. Yeah. And so in this case, if you're 12K per minute rate and above, you make glass, and 5 and below, you consistently make crystalline, and in between that is kind of the gray area that
no, it's great you're catching the phase transition or whatever you want to call it there of between the two. Very good.
Yeah. And so just between these two sets of experiments alone, begins to develop a trend in which the lower the brine concentration is, the easier it is to make glass. So we'll go a bit into detail on possibly why that is a bit later on.
Okay. Great.
Oh, do you want to take us?
And I should maybe just point out, Tuan, is that sort of that we're starting out with 2 molar concentrations, and as Tuan had sort of suggested, that's actually pretty salty. And I don't think it's meant to indicate that we think that is the concentration, but what we want to do is when it's a bit of an exploratory experiment, so we start at a concentration that we know we're going to see something, and then we can sort of lower it down, because at some point you lower the concentration enough when we're just not seeing the signals that we're using to trace these the form of the salts. So
that would be a problem.
Yeah. But I mean, so that's just sort of that's where 2 molar came from.
Yeah, and I'll add to that as well. While we're on this page, is that in the magnesium sulfate case in table 2, we were able to do the experiment at the lower end at 0.1 molar. Of course, for macrolide, we also tried to do 0.1 molar, but since the chloride itself doesn't have a vibrational signature, when we did the 0.1, it was too low to detect any changes in the water. And so we have to ramp it up to 0.5.
0.5. Yep.
Just in this case. So yeah.
Well, that's interesting. Okay.
Yeah.
Okay.
Yeah.
I'll have the questions later. Okay. Good. Good.
Yeah.
Okay, so I guess figure 3 is
Figure
where we're
3?
going next.
Yes. And figure 3, and there we go.
Okay, so this is where we're changing to a different salt here. So we're using sodium sulfate, or is what we're forming here. So this spectrum we see here is a 0.1 molar concentration of sodium sulfate, that we froze at 100 K. And as you see here on the inset, again, what's nice about it's the sulfate. So we have this nice sort of characteristic peak at around 990 in the sulfate. But what we see here is these, it's the crystalline form. It's the nice sharp peak centered around 990. And let's see, this was from a flash frozen sample. Okay, so even with, what was interesting with the sodium sulfate is that even when we flash froze it, we formed the crystal. We did not get, we were never creating a glass of sodium sulfate.
Gotcha.
So interesting compared to sort of the magnesium sulfate, which we formed quite readily.
Right.
And so that's kind of interesting because it's just a change in the positive ion. Right. And I guess, Tuan, do you want to go on to the fourth one?
Yep. Yeah. And of course, out of the 4 ions, we have 4 possible combinations of salt. So we've seen the other 3. The last one is sodium chloride.
Right.
Again, with the chloride, we can't see it by itself. So we're looking at the water region.
Yeah.
So again, blue is flash frozen. Red is in this case 50 degrees per minute freezing. And so you only make glasses in this case when you flash freeze it.
Right.
And the red one, the peaks that you see around 3400, those are characteristic of hydrohalite, which is one of the species that has tentatively been detected for Europa.
Really? Okay.
Some of my colleagues here at JPL have looked at the change in sodium chloride upon radiation, and thought that they could explain, like the yellow brownish feature that you often see for Europa. So it's thought to be it's thought to be from irradiated sodium chloride. So
you're getting photochemical. Yeah,
exactly. So this case, just like the other, the other one, the transition is the transition zone is somewhere between flash freezing, which is tens of degrees per second, and 50 degrees per minute. Okay. But we're also unable to pinpoint that exactly as of now.
We'll have questions later. Okay, very good.
All right. So this thing, at this stage, I think we can discuss a bit on the observed behavior and propose some rationale on why this could be happening. So Paul, you want to take the first one with the
okay. Sure. So let's see here. So the first thing we see here is that, I guess the first thing we mentioned is that glasses are forming. The faster you freeze things, the more likely you are to get a glass. Which I don't think this isn't a big revelation here, but our observations follow what the expectation is. And basically what you see here is when things are going slowly, right, ions in solution are able to look around and find the partner they want to dance with to be in their lowest energy configuration, in their preferred state. Whereas if you freeze it fast enough, then they're kind of locked in place before they can arrange themselves in their preferred way. So nothing revolutionary there, but it follows what we expect. Then I guess the next thing we see here is that at lower concentrations, right, we saw this in the data we talked about, is that you are able to form glasses at slower freezing rates.
Right.
And I think maybe maybe the rationale behind that is that when you have fewer of them in the solution, as they're, things are cooling down and they're trying to find their partners and form their crystal, if the partner's harder to find, it's harder to get the crystal to start and to form.
Got it.
Right.
Yeah, makes sense.
So that's, it seems reasonable. Then I guess the final thing that was fairly apparent also was sort of the propensity for mag chloride cations to form the glasses versus the sodium, which we found, well, in sodium sulfate, we couldn't make the glass. And with sodium chloride, it was only when we flash froze it. So it's considerably, or our observations indicate that it's much more difficult for the sodium salts to form glasses. And maybe I'll pass off this one to Tuan.
Yeah, and so if you think about how these processes come about, when you're in solution, the ions are completely separated from each other, right? So you have your cation surrounded by a bunch of water to make a hydration shell. Your anion is surrounded by its own hydration shell. And so for a salt crystal to form, these ions have to break through the water barrier to find their partners and crystallize out. In the case of sodium versus magnesium, magnesium is, first of all, a 2+ charged ion. Sodium is 1+. And magnesium is also a smaller cation than sodium. So you have a really high charge density particle that's trying to break. That's bounded very strongly to the hydration shell, and so it's going to be considerably harder for the sulfate to come and find it. Whereas the sodium has a relatively weaker hydration shell, and so it forms a crystal easier. And so we found some values of these energies in the literature. The enthalpy of hydration for magnesium is roughly about 5 times that. So, 5, And so that we think that explains the behavior that we're seeing.
Cool.
So these 3 trends are the main findings of the paper. And
very cool. Very cool. That's going to lead me to all kinds of good questions. But first of all, Paul and Tim, thank you so much for walking us through your very lovely PSJ article. I learned several things. So very cool. Very cool. So let me ask, where do you think we go over the next 2 to 5 years? On the laboratory astrophysics, I think you mentioned, a couple limitations of the hardware right now. You can't get your freezing rates maybe as fast as you would want them to. Maybe the pressures aren't the full range you want to cover. Maybe the ability to step even finer to maybe resolve those phase transitions between the two. So are there improvements planned on the experimental apparatus? And is there maybe some mission data that can help inform what some of those compositions are and so on? So just sort of where do we go over the next, let's say, 2 to 5 years?
So I would say, and Tuan, you can weigh in if you disagree with me. I would say all of those things you point out are true, right? But I think in sort of in the broader picture of its application to an ocean world and fluids freezing and being exposed on the surface, being able to pinpoint it to within a degree per minute at freezing rate is probably not.
Okay.
We probably don't understand how things are working good enough for that to really matter. Do you know what I'm saying?
Yes.
Or at least at this stage. I think right now what comes out of this work is that not only do these glasses form, but they seem to form. They don't have to have this extreme freezing scenario to form. So then the likelihood that they're going to be found and formed and found on these bodies is probably more widespread than if we were just limiting it to like a plume scenario. Okay. So if you take that view that these these are likely to be on the surface, or to at least be created on the surface, then the question is like, what is the, how stable are they? Do they sit for 5 minutes and crystallize and then it doesn't matter, or does it sit around there for a million years? You know, in which case, you know, you might actually find it, right? And so we've actually we're just wrapping up some experiments where we've looked at kinetics of crystallization of these glasses, trying to poke at that idea as how stable are they? And you know, we expect them to form, but do we expect them to stay around long enough for them to matter? Yeah. Sure. And then I guess, I don't know, Tuan, if you want to go talk about other steps.
Yeah. So basically, yeah, like Paul said, we're finalizing an upcoming paper describing how stable these glasses are. So you know, one other line of experiment we have been pursuing as well is to put some microbial bugs into.
Yeah, I was gonna go there. Good. Yeah.
See whether they can survive and have a higher possibility of being
that's cool.
Volatile, and protected in these glasses material. So we have done some experiments on that with very promising results, and I would expect that we would be able to report this in a very near future.
I'm going to take that positive result as meaning they all didn't die.
And you know, and I think it's really exciting, right? In the sense that if there's a hope of finding extant life on one of these bodies, you know, one of the issues about, you know, with astrobiology, I think, is what is proof, right? What will we find that is convincing that there is either past or present life on it, right? But if you were able to, you know, thaw out a sample of ice and actually, with, you know, say with a microscope, see a microorganism swimming around, I think that would convince a lot of people that, you know, you might have to argue about, did you bring it with you or something? You know, there's always that kind of question. But, you know, if you could identify a place where you would think that if an organism wasn't trained in it, there's a reasonable chance that it might actually not only be preserved physically, but actually be viable, would be, you know, I think that's pretty exciting.
Yeah, very.
And so, you know, like Tuan said, is that I think, you know, or I think I'd said in the beginning, you know, it's how should we expect these things to form widespread? If they do, how long do they stick around? And is this viability idea, you know, does it really pan out, right? Awesome. And in particular, in terms of the salts and species that you would expect on this body, because I think, you know, the idea of cell preservation in glassy materials that's a fairly established thing. And, you know, when you store cell stocks or whatever in. Right.
Cool. Very nice. Well, I really look forward to seeing those results coming up soon. You teased me with that one too.
Yeah.
I look forward to seeing that.
Yeah, I think, and we can top this off with an implication for other oceans.
Okay.
Other ocean worlds as well. Like we have been very focused on Europa because that's what we've been studying for many years. But you know, there's no reason why you know, this sort of idea cannot exist on other bodies. In fact, there was a study just last year looking at analog brines for Enceladus, and they too were able to form glasses under certain freezing conditions. And so you can you know, see the implication this may have for Enceladus plume, possibly extruding microbial bugs in there, and what that could mean for Orbilander. And yeah, that's all seeming very exciting and enticing venture.
Absolutely.
For us, so.
Absolutely, especially if some of those plumes reach escape velocity, and now you're propagating. Very Very cool. Very cool. All righty, Paul, Tuan, thank you so much again for walking us through your very lovely article. And everyone, I hope this made your astronomy day and your planetary science day just a little bit better, and we will see you on the next one. Bye-bye.
Bye-bye. Thanks for having us.
Thank you.